Hi everyone. I'm Tamogno Hazra. I'm a postdoc at Rutgers University in the group of Piers Coleman, and today I'll be talking about Luttinger Sum Rules in SUN invariant Kondo Hamiltonians. First, I'll present an exact result for the Fermi surface volume in SUN Kondo models. This is a direct extension of Ushikawa's construction for SU2, following earlier work by Liebschulte, Mattis, and others. Extending this theorem to arbitrary n allows us to connect to the large n limit and the intuition from mean field theory. And lastly, I'll explore some of the implications of this construction for the volume of the spin-on Fermi surface in U1 spin liquids. And I'll suggest a simpler way to understand the small Fermi surface in the FL star regime. Now, the Kondo lattice model is a lattice of spins immersed in a conduction sea of electrons. As a result of the coupling, the spins ionize into heavy fermions, which join the conduction sea. The resulting expansion of the Fermi surface is supported by the experimental observation of a jump in the magneto-oscillation frequencies as you enter the Kondo-coupled heavy Fermi liquid. Now, this has long been one of the fruit fly models of our understanding of strongly correlated matter, and relatively recently, we've also learned about the possibility of T-confined quantum critical points separating the heavy Fermi liquid from local moment magnetism. There are two limits in which our theoretical understanding of this model is grounded. There's a rigorous theorem for the Fermi surface volume in SU2, and in the large n limit, there's mean field theory, which becomes exact. And our goal is to connect these two by extending Ushikawa's theorem to arbitrary n. The first step is to put the system on a torus and to thread through one of the holes of the torus a quantum of gauge flux that only couples to one of the n flavors of fermions. We can do this without ever breaking lattice translation. So the ground state evolves to an excited state with the same canonical momentum. Now, since this is a gauge symmetry, the new Hamiltonian is unitarily equivalent to the old one, and we can use this unitary transformation to go back to the initial gauge. And evaluating the momentum of the final state in the initial gauge tells us what is the change in physical momentum as a result of this flux insertion. In a Fermi liquid, the response to a flux insertion is straightforward. Each state in the field Fermi C picks up an additional momentum of A, the vector potential, and this allows us to relate the response to the momentum that we calculated earlier to the Fermi surface volume. The key step in computing the momentum response is to identify this unitary transformation that couples a one unit of flux quantum to just one flavor of the fermions while preserving lattice translation invariance. Now, we found this unitary transformation, but before I tell you what it is, I need to set up some notation. So here's the Hamiltonian. It describes fermions with degeneracy n, say that it's in a multiplet with angular momentum j. The electrons hop through the lattice and interact with the local moments represented by lambda. Each of the local moments transforms according to the antisymmetric representation of SUN depicted by this Young tableau. And we put in a Piles phase coupled to one of the n flavors as required. So the challenge then is to find a unitary transformation of the Hamiltonian that will inject this vector potential into one of the flavors without affecting the Kondo term. We found such a unitary transformation that inserts the flux that works for arbitrary n. And the key point is that to keep the Kondo term invariant, the gauge transformation must include a spin twist. Now, if we use this unitary transformation to calculate the momentum response to the flux insertion, that immediately leads to the Fermi surface volume. The Fermi surface volume counts the electron density, and for SUN, an additional factor Q over n that accounts for the local moments. Now, this is an exact result valid for arbitrary n. We can, of course, do this separately for each flavor because there's a U1 symmetry for each flavor of fermions. But for SUN invariant states, this is the central result that I wanted to communicate with you today. And now I'm going to end the talk by talking about some implications of this result. First, if you stare at this result and you remember what the right-hand side represents, you realize there's something bizarre. Localized spins contribute momentum. Twisting the spin imparts physical momentum to the system. So we'd like to understand this better. And since our result holds exactly for arbitrary n, it also holds in the large n limit, where we can explicitly see the flux insertion acting on the mean field ground state, which becomes exact in this limit. Now we can always represent the spin by because of fermions with a local constraint on the local fermion occupation. Finite mean field results in hybridization of the C fermions, the electrons, with the F fermions, the spinons. As a result, the U1 gauge of the spinons gets locked to the electromagnetic gauge, and by this mechanism, the spinons acquire charge. The hybridized spinons then occupy this enlarged Fermi surface, and when you insert flux, each fermion, whether C fermion or F fermion, gets boosted by a flux insertion. And so the Fermi surface counts all of the filled states, regardless of whether they were originally electrons or fractionalized from spins. The key point here is that the spinons exist independently in this large Fermi surface and can be probed independently, whereas the local moment was a composite of Q fermions. Now, if you extend this picture of spin fractionalization from large n to arbitrary n, what that buys you is a simple intuitive understanding of this bizarre momentum response. The local moments fractionalize into spinons. The unitary transformation imparts equal momentum to both species of fermions, which is why you have an expanded Fermi surface. Having explicitly seen how this works in the large and mean field theory allows us to understand how the spin flux, which couples to the localized spins, can impart additional momentum to the system. We realize that this prescription works just as well for a pure Heisenberg model. The spin twist imparts momentum to the abricos of fermions. And if you're in a ground state with no broken symmetries and the spinons occupy an incompressible Fermi surface, then we can show that the volume of the spin-on Fermi surface is given by Q over N, the filling of the spinons. And for the SU2 case, this was also recently shown by Stelzay, Thorngrain, and Senthal. Now, lastly, we'd like to touch upon this very enigmatic FL star phase of FL star regime of the Kondo lattice models, in which the Fermi surface volume counts only the electrons. In earlier literature, the FL star phase has been discussed as harboring an instance of a very interesting topological state, the fractionalized Z2 spin liquid, threading a flux through the torus creates a vortex with momentum pi over L called the Vizon. And this takes the system between two topological sectors, one in which there is or isn't a pi flux threading the torus. An alternative interpretation of FL star is simply two decoupled liquids with their own independent Fermi surface. You can thread a spin flux and get the spin-on Fermi surface, or you can thread a charge flux and get the electron Fermi surface. And since the U1 phase of the spin-ons and the electrons are decoupled, the momentum response to an electromagnetic field does not include the spin-ons. In fact, you can see that both of these gauge transformations respect periodic boundary conditions. So there are no Vizons on the boundary and no topological order in this picture. So to sum up, one of the few exact results in Kondo systems is a non-perturbative proof by Oshikawa of the Fermi surface volume, which includes both electron and spin densities. We extended this theorem to arbitrary from SU2 to SUn for arbitrary n, and we present exact expressions for the Fermi surface volume, not only for the heavy Fermi liquid with a large Fermi surface, but also for the small Fermi surface of the mysterious FL star regime and the spin-on Fermi surface in a pure spin Hamiltonian, in a pure spin Hamiltonian with a spin liquid ground state. Extension to arbitrary n allows us to connect to the large and mean field intuition. We understand the Kondo effect as a fractionalization of local moments into spin-ons, followed by a gauge coupling of the fractionalized spin-ons to the electrons. A failure of this gauge coupling presents a simple interpretation of the enigma of the FL star regime without invoking topological order.